The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Thank you. So, okay, let's continue with vectors and operations on them. So remember, yesterday, we saw the topic yesterday was dot product. And remember the definition of dot product? Well, the dot product of two vectors is obtained by multiplying the first component with the first component, the second with the second, and so on, and summing these, and you get a scalar. And the geometric interpretation of that is that you can also take the length of A, take the length of B, multiply them, and multiply that by the cosine of the angle between the two vectors. So we've seen several applications of that. So one application is to find lengths and angles. So for example, well, you can use this relation to give you that the cosine of the angle between two vectors is their dot product divided by the product of the lengths. Another application that we have is to detect whether two vectors are perpendicular. So to decide if two vectors are perpendicular to each other, all we have to do is compute their dot product and see if we get 0. Okay. And well, one third application that we didn't have time to discuss yesterday, but I will mention very quickly, is to find components of, so let's say find the component of a vector A along a direction U, so some unit vector. So let me explain. Let's say that I have some direction, for example, the horizontal axis on this blackboard, but it could be any direction in space. And to describe this direction, maybe I have a unit vector along this axis. Let's say that I have any other vector A, and I want to find out what is the component of A along U. So that means what is the length of this projection of A to the given direction. Okay, so this thing here is the component of A along U. Well, how do we find that? Well, we know that here we have a right angle, so this component is just length A times cosine of the angle between A and U. But now that means actually we can compute it very easily because, well, I could, that's the same as length A times length U times cosine theta, because U is a unit vector. It's a unit vector. That means this is equal to 1. And so that's the same as the dot product between A and U. Okay? So that's very easy. I mean, of course, the most obvious cases of that is, say, for example, we want just to find the component along I hat, the first axis, the unit vector along the x-axis. Then you do the dot product with I hat, which is 1, 0, 0. What you get is the first component. and that's indeed the x component of a vector. Similarly, say you want the z component, you do the dot product with k, that gives you the last component of your vector. But the same works with a unit vector in any direction. Okay, so what's an application of that? Well, for example, in physics, maybe you have seen situations where you have a pendulum that swings. So you have maybe some mass at the end of a string, and that mass swings back and forth on a circle. And to analyze this mechanically, you want to use, of course, Newton's laws of mechanics, and you want to use, well, forces and so on. But I claim that components of vectors are useful here to understand what happens geometrically. So what are the forces exerted on this pendulum? Well, there's its weight, which usually points downwards. And there's the tension of the string, and these two forces together are what explains how this pendulum is going to move back and forth. Now, you could try to understand the equations of motion using xy coordinates, or maybe xz, or whatever you want to call them. Let's say xy. But really, what causes the pendulum to swing back and forth, and also to somehow stay at constant distance, are phenomena relative to this circular trajectory. So, for example, maybe instead of taking components along the x and y axes, we want to look at two other unit vectors. So we can look at a vector, let's call it t, that's tangent to the trajectory. Sorry, can you read that? Maybe it's not very readable. So t is tangent to the trajectory. And on the other hand, we can introduce another vector. Let's call that n. And that one is normal or perpendicular to the trajectory. And so now, if you think about it, you can look at the components of the weight along the tangent direction and along the normal direction. And so the component of F along the tangent direction is what causes acceleration in the direction along the trajectory. It's what causes the pendulum to swing back and forth. And the component along n, on the other hand, so that's the part of the weight that tends to pull our mass away from this point, is what's going to be responsible for the tension of the string. It's why the string is taut and not actually slack and with things moving all over the place. So that one is responsible for the tension of a string. And now, of course, if you want to compute things, well, maybe you will call this angle theta, and then you will express things explicitly using sines and cosines, and you will solve for the equations of motion. Okay, that would be a very interesting physics problem, but to save time, we're not going to do it. I'm sure you've seen that in 801 or similar classes. And so to find these components, we would just do dot products. Okay, any questions? No? Okay, so let's move on to our next topic. So here we have found things about lengths, angles, and stuff like that. One important concept that we haven't understood yet in terms of vectors is area. So let's say that we want to find the area of this pentagon. Well, how do we compute that using vectors? Can we do it using vectors? Yes, we can, and that's going to be the goal, but how? So the first thing we should do is probably simplify the problem. We don't actually need to bother with pentagons. All we need to know are triangles. Because, for example, you can cut that into 3 triangles and then sum the areas of the triangles. OK, so perhaps easier, what's the area of a triangle? So let's start with a triangle in the plane. And, well, then we need 2 vectors to describe it, say A and B here. How do we find the area of a triangle? Well, we all know base times height over 2. So what's the base? What's the height? Well, so the area of this triangle is going to be 1/2 of the base is going to be the length of A. And the height, well, if you call theta this angle, then this is length B sine theta. Now, that looks a lot like the formula we had there, except for one little catch. This is a sine instead of a cosine. How do we deal with that? Well, what we could do is first find the cosine of the angle. We know how to find the cosine of the angle using dot product. Then solve for sine using sine square plus cosine square equals 1. And then plug that back into here. Well, that works, but it's kind of a very complicated way of doing it. So there's an easier way. Okay, and that's going to be determinants. But let me explain how we get to that, maybe still doing elementary geometry and dot products first. So let's see. What we can do is instead of finding the sine of theta, well, we're not good at finding sines of angles, but we are very good now at finding cosines of angles. So maybe we can find another angle whose cosine is the same as the sine of theta. Well, you've probably heard about complementary angles and how, if I take my vector A, I have my vector B here, I have an angle theta. Well, let's say that I rotate my vector A by 90 degrees to get a new vector A prime. Okay, so A prime is just A rotated by 90 degrees. Then the angle between these two guys, let's say theta prime, well, theta prime is 90 degrees or pi over 2 radians minus theta. So in particular, cosine of theta prime is equal to sine of theta. Okay. So in particular, that means that length A, length B, sine theta, which is what we would need to know in order to find the area of this triangle, is equal to, well, A and A prime have the same length. So let me replace that by length of A prime. Okay, I'm not changing anything. Length B, cosine theta prime. And now we have something that's much easier for us, because that's just A prime dot B. Okay, so that looks like a very good plan. There's only one small thing, which is we don't know yet how to find this A prime. Well, I claim it's not very hard. Let's see. Actually, why don't you guys do the hard work? So let's say that I have a plane vector A with two components, A1, A2, and I want to rotate it counterclockwise by 90 degrees. So it looks like maybe we should change some signs somewhere. Maybe we should do something with the components. Can you come up with an idea of what it might be? OK, so I see a lot of people answering 3. I see some other answers, but the majority vote seems to be number 3, minus A2 and A1. I think I agree. So let's see. Let's say that we have this vector A with components A1, so A1 is here, and A2, so A2 is here. Okay, let's rotate this box by 90 degrees counterclockwise. So this rectangular box ends up there. It's the same box, just flipped on its side. So this length here becomes A1, and this length here becomes A2. And that means our new vector A prime is going to be, well, the first component looks like an A2, but it's pointing to the left when A2 is positive. So actually, it's minus A2. And the y component is going to be the same as this guy, so it's going to be A1. Okay. If you wanted instead to rotate clockwise, then you would do the opposite. You would do A2 minus A1. Okay. Is that reasonably clear for everyone? Okay. So, well, let's continue that calculation there. A prime we've decided is minus A2, A1. So minus A2, A1, dot product with, let's call B1 and B2 the components of B. Then that will be, well, minus A2, B1 plus A1, B2. Let me write that the other way around. A1, B2 minus A2, B1. And that's a quantity that you may already know under the name of determinant of vectors A and B, which we write symbolically using this notation. So we put A and B next to each other inside a 2x2 table, and we put these vertical bars, and that means the determinant of these numbers. It means this guy times this guy minus this guy times this guy. Okay? So that's called the determinant. And geometrically, what it measures is the area, well, not of a triangle because we didn't divide by 2, but of a parallelogram formed by A and B. So it measures the area of the parallelogram with sides A and B. And of course, if you want the triangle, then you will just divide by 2. Okay, the triangle is half a parallelogram. There's one small catch. The area usually is something that's going to be positive. This guy here has no reason to be positive or negative because, in fact, well, if you compute things, you will see that whether it's positive or negative depends on whether A and B are clockwise or counterclockwise from each other. I mean, the issue that we have, well, when we say the area is 1/2 length A, length B sine theta, that was assuming that theta is positive, that its sign is positive. Otherwise, if theta is negative, maybe we need actually to take the absolute value of this. So just to be more truthful, I will say the determinant is either plus or minus the area. Okay. Any questions about this? Yes?
You're discussing dot product of A, B, sine theta. What exactly is that equal to?
Oh, sorry, that's not a dot product. That's a usual multiplication. Okay? That's length A times length B times sine theta.
What is that equal?
And so that's equal to the area of a parallelogram. So let me explain that again. So if I have two vectors A and B, so I can form a parallelogram with them, or I can form a triangle. Okay? And so the area of a parallelogram is equal to length A, length B, sine theta is equal to the determinant of A and B. While the area of a triangle is 1/2 of that. And again, to be truthful, I should say these things can be positive or negative. So depending on whether you count the angle positively or negatively, you will get either the area or minus the area. The area is actually the absolute value of these quantities. Okay, is that clearer? Okay. Yes, sorry.
You said the determinant could be negative or positive. How do you fix it?
So if you want to compute the area, you will just take the absolute value of a determinant. Okay? So area will be well, I should say the area of a parallelogram so that it's completely clear. Sorry, you have also a question? Yeah. Explain again, sorry, what's the question? How the determinant equals the area of a parallelogram? Okay, so the area of a parallelogram, it's going to be the base times the height, right? So the base, let's take this guy to be the base. So the length of the base will be length of A. Then the height will be obtained by taking B, but only looking at the vertical part. So that will be length of B times the sine of theta. Okay, so that's how I got that the area of a parallelogram is length A, length B, sine theta. And then I did this manipulation and this trick of rotating to find a nice formula. Yes? So you're asking ahead of what I'm going to do in a few minutes. So you're asking about the magnitude of A cross B. So we're going to learn about cross product in a few minutes. And the answer is yes, but cross product is for vectors in space. Here I was simplifying things by doing things just in the plane. Okay, so just bear with me for 5 more minutes and we'll do things in space. Yes? That's correct. The way you compute this in practice is you just do this. Okay, that's how you compute a determinant. Yes? What about? So 3 dimensions we are going to do now. Okay? More questions? Should we move to? Okay, let's move to space. So there's 2 things we can do in space. And you know, you can look for the volume of solids or you can look for the area of surfaces. So let me start with the easier of the 2. Let me start with volumes of solids. And we'll go back to area, I promise. So I claim that there's also a notion of determinant in space, and that's going to tell us how to find volumes. So let's say that we have three vectors, A, B, and C. And then the definition of their determinant is going to be, so the notation for that in terms of the components is the same as over there. We put the components of A, the components of B, and the components of C inside vertical bars. Okay? And of course, I have to give a meaning to this. So this will be a number. And what is that number? Well, the definition I will take is that this is A1 times the determinant of what I get by looking in this lower right corner. So the 2 by 2 determinant, B2, B3, C2, C3. Then I will subtract A2 times the determinant of B1, B3, C1, C3. And then I will add A3 times the determinant B1, B2, C1, C2. And each of these guys means, again, you take B2 times C3 minus C2 times B3. And this times that minus this times that, and so on. So in fact, there's a total of 6 terms in here. Okay, and maybe some of you have already seen a different formula for 3 by 3 determinants where you directly have the 6 terms. It's the same. Okay, it's the same definition. So how to remember the structure of this formula? Well, this is called an expansion according to the first row. So we're going to take the entries in the first row, A1, A2, A3, and for each of them, we get a term. Namely, we multiply it by a 2 by 2 determinant that we get by deleting the first row and the column where we are. Okay, so here, the coefficient next to A1 is, well, we delete this column and this row, and we're left with B2, B3, C2, C3. Next, the next one, we take A2, we delete the row that's in it and the column that it's in, and we're left with B1, B3, C1, C3. And similarly with A3, we take what remains, that's B1, B2, C1, C2. Finally, last but not least, there's a minus sign here for the second guy. Okay? So, well, it looks like a weird formula. And I mean, it is a little bit weird, but it's a formula that you should learn because it's really, really useful for a lot of things. So I should say, if this looks very artificial to you and you'd like to know more, there's more in the notes. So read the notes. They will tell you a bit more about what this means, where it comes from, and so on. If you want to know a lot more, then someday you should take 1806, linear algebra, where you will learn a lot more about determinants in n-dimensional space with n vectors. And there's a generalization of this in arbitrary dimensions. In this class, we'll only deal with 2 or 3 dimensions. Yes? Sorry, why is the negative there? Well, that's a very good question. It has to be there so that this will actually equal, well, what I'm going to say right now is that this will give us the volume of the box with sides A, B, C. And the formula just doesn't work if you don't put the negative. There's a more fundamental reason which has to do with orientation of space and the fact that if you switch 2 coordinates in space, then basically you change what's called the handedness of the coordinates. If you look at your right hand and your left hand, they are not actually the same. They're mirror images. And if you swap 2 coordinate axes, that's what you get. That's the fundamental reason for the minus. But again, I mean, we don't need to think too much about that. All we need in this class is the formula. So why do we care about this formula? It's because of a theorem that says that geometrically, the determinant of the 3 vectors A, B, C is, again, plus or minus this determinant could be positive or negative. See, there's minuses and there's all sorts of stuff. Plus or minus the volume of the parallelepiped. That's just a fancy name for a box with parallelogram sides, in case you wonder. With sides A, B, and C. Okay, so you take your three vectors A, B, and C, and you form a box whose sides are all parallelograms. And then its volume is going to be the determinant. Okay. Other questions? Oh, at the back. I'm sorry, I can't quite hear you. Yes, we are going to see how to do it geometrically without a determinant, but then you'll see that you actually need a determinant to compute it, no matter what. So we are going to go back to this and see another formula for volume, but you'll see that really I'm cheating. I mean, the important way, I mean, somehow computationally, the only way to compute it is really to use a determinant. Yes? That's correct. In general, I mean, actually, I should say, if you look at the 2 by 2 determinant, see, you can also explain it in terms of this expansion. You take A1 and multiply by this 1 by 1 determinant B2. Then you take A2, you multiply it by this 1 by 1 determinant B1, but you put a minus sign. And in general, indeed, when you expand, you would start putting plus, minus, alternatingly. More about that in 1806. Yes? There's a way to do it based on other rows as well, but then you have to be very careful with the sign factors. So I'll refer you to the notes for that. Okay, if you did it with, I mean, you could also do it with a column, by the way. Just, I mean, be careful about the sign rules. So given how little we'll use determinants in this class, I mean, we'll use them in a way that's fundamental, but we won't compute much. So let's say this is going to be enough for us for now. Okay, so after determinants, now I can tell you about cross product. And cross product is going to be the answer to your question about area. Okay, so let me move on to cross product. So cross product is something that you can apply to two vectors in space. And by that I mean really in three-dimensional space, okay? This is something that's specific to 3 dimensions. So the definition, A cross B, so it's important to really do your multiplication symbol well so that you don't mistake it with a dot product. Well, that's going to be a vector okay, so that's another reason not to confuse it with dot product. Dot product gives you a number, cross product gives you a vector. So they're really completely different operations. They're both called product because, well, somehow one couldn't come up with a better name, but they're completely different operations. Okay, so what do we do to do the cross product of A and B? Well, we do something very strange. Just after I've told you that a determinant is something where we put numbers and we get a number, I'm going to violate my own rule. I'm going to put together a determinant in which, well, the last two rows are the components of the vectors A and B, but the first row, strangely, consists of the unit vectors I, j, k. What does that mean? Well, that certainly is not a determinant in the usual sense. You cannot, if you try to put that into your calculator, it will tell you there's an error. I don't know how to put vectors in there. I want numbers. What it means is it's a symbolic notation that helps you remember what the formula is. So the actual formula is, well, you use this definition. And if you use this definition, you see that it's I hat times some number. Okay, so let me write it as determinant of A2, A3, B2, B3 times I hat minus determinant A1, A3, B1, B3, J hat plus A1, A2, B1, B2, K hat. Okay? And so that's the actual definition in a way that makes complete sense. But to remember this formula without too much trouble, it's much easier to think about it in these terms here. Okay, so that's a definition. And it gives you a vector. Now, as usual with definitions, the question is, what is it good for? What is the geometric meaning of this very strange operation? Why do we bother to do that? So here's what it does geometrically. So remember, a vector has two different things. It has a length and it has a direction. Okay, let's start with the length. The length of a cross product is the area of the parallelogram in space formed by the vectors A and B. Okay? So now if you have a parallelogram in space, you can find its area just by doing this calculation when you know the coordinates of the points. You do this calculation, and then you take the length. So the length, you take this squared plus that squared, square root. It looks like a very complicated formula, but it works, and actually it's the simplest way to do it. Okay. This time we don't actually need to put plus or minus, because the length of a vector is always positive. We don't have to worry about that. And what's even more magical is that not only is the length remarkable, but the direction is also remarkable. So the direction of A cross B is perpendicular to the plane of a parallelogram. So, our two vectors A and B together they determine a plane. And what I'm telling you is that the vector A cross B will stick straight out of that plane, perpendicularly to it. Okay. So in fact, I have to be more precise. There's two ways that you can be perpendicular to this plane. Right? You can be perpendicular pointing up or pointing down. How do I decide which? Well, there's something called the right-hand rule. Okay, so what does the right-hand rule say? Well, there's various versions of the right-hand rule depending on in which country you learn about it. In France, given the culture, you even learn about it in terms of a corkscrew and a wine bottle. But I think I'll just use the usual version here. So you take your right hand. If you're left-handed, remember to take your right hand, not the left one, the other right. Okay? And then place your hand to point in the direction of A. So let's say my right hand is going in that direction. Now, curl your fingers so that they point towards B. So here that would be kind of into the blackboard. Okay? Don't snap any bones. If it doesn't quite work, then rotate your arm so that you can actually physically do it. Then get your thumb to stick straight out. Well, here my thumb is going to go up, and that tells me that A cross B will go up. Okay? So let me write that down while you experiment with it. Again, try not to injure yourselves. So first, your right hand points parallel to vector A. Then your fingers point in the direction of B. Then your thumb, when you stick it out, is going to point in the direction of A cross B. Okay? Let's do a quick example. Where's my quick example? Here. Let's take I cross J. So I see some of you, well, most of you have it going in the right direction. If you have it pointing in the wrong direction, it might mean that you're using your left hand, for example. Okay. So, example, I claim that I cross J equals K. Okay? Let's see. I points towards us. J points to our right. So I guess this is your right? I think. It's kind of hard to. And then your thumb is going to point up. Okay? So that tells us it's roughly pointing up. And of course, the length should be 1, because if you take the unit square in the xy plane, its area is 1. And the direction should indeed be vertical, because it should be perpendicular to the xy plane. So it looks like I cross J will be K. Well, let's check with a definition. IJK, what is I? I is 1, 0, 0. J is 0, 1, 0. Well, so the coefficient of I will be 0 times 0 minus 0 times 1, that's 0. Coefficient of J will be 1 times 0 minus 0 times 0, that's 0, minus 0J, doesn't matter, but. And the coefficient of K will be 1 times 1, that's 1, minus 0 times 0, so 1K. Okay? So we do get I cross J equals K both ways. In this case, it's easier to do geometrically. If I give you more complicated vectors, probably you will actually want to do the calculation. Okay, any questions? Yes?
Real quick, how did you figure out the 1 times 1 in the last?
So the coefficient of K, remember I delete the first row and the last column. So I get this 2 by 2 determinant. Okay, and that 2 by 2 determinant is 1 times 1 minus 0 times 0. So that gives me 1. Okay? That's what you do with 2 by 2 determinants. Similarly for the others, but the others turn out to be 0. More questions? Yes, let me repeat how I got the 1 in front of K. So remember the definition of a determinant. I expand according to the entries in the first row. When I get to K, what I do is I delete the first row, and I delete the last column, the column that contains K. Okay? So I delete these guys and these guys. I'm left with this 2 by 2 determinant. Now, a 2 by 2 determinant, you multiply according to this downward diagonal, and then minus this times that. Okay, so 1 times 1.
1K.
Let me say here, I got 1K because that's 1 times 1 minus 0 times 0 equals 1. Sorry, and that's really hard to read. Maybe it will be easier that way. Okay. Yes?
So for I and j, do the same, because it seems that if you do the same with I, you will get -1.
Okay, so let's try. If I do the same for I think I will also get 0. Okay, so let's do the same for I. So I take I delete the first row, I delete the first column, I get this 2 by 2 determinant here, and I get 0 times 0, that's 0, minus 0 times 1, that's here the trick question. 0 times 1 is 0 as well. So that's 0 minus 0 is 0. Okay? So I hope in Monday you should get more practice in recitation about how to compute determinants. So hopefully it will become very easy for you all to compute these things. I know the first time it's kind of a shock because there's a lot of numbers and a lot of things to do. Not good. Okay. So let me return to the question that you asked a bit earlier about how do I find actually volume if I don't want to know about determinants. Well, so let's have another look at the volume. Okay? So let's say that I have 3 vectors. Let me put them this way, A, B, and C. And let's try to see how else I could think about the volume of this box. Okay? So probably you know that the volume of a parallelepiped is the area of a base times the height. Okay? So, sorry, the volume is the area of a base times the height. How do we do that in practice? Well, what's the area of a base? So the base is a parallelogram in space with sides B and C. How do we find the area of a parallelogram in space? Well, we just discovered that. We can do it by taking the cross product. So the area of a base, well, we take the cross product of B and C. That's not quite it, because this is a vector. We would like a number. Well, we take its length. Okay? That's pretty good. What about the height? Well, the height is going to be the component of A in the direction that's perpendicular to the base. So let's take a direction that's perpendicular to the base. Let's call that n, a unit vector in that direction. Then we can get the height by taking A dot n. That's what we saw at the beginning of class. Okay, that A dot n will tell me how much A goes in the direction of n. Okay, are you still with me? Okay, let's keep going. So let's think about this vector n. How do I get it? Well, I can get it by actually using cross product as well. Because I said the direction perpendicular to 2 vectors I can get by taking the cross product and looking at that direction. So this is still B cross C length. And this one is, so I claim, maybe I should do an aside here, n can be obtained by taking B cross C, well, that points in the right direction, but it's not a unit vector. How do I get a unit vector? I divide by the length. Thanks. So I take B cross C, and I divide by length B cross C. Well, now I can probably simplify between these two guys. And so what I will get it's going to be the last thing for today. What I get out of this is that my volume equals a dot product with the vector B cross C. And of course, I have to be careful in which order I do it. If I do it the other way around, A dot B, I get a number. I cannot cross that. So I mean, I really have to do the cross product first. I get a new vector, and then I dot product. OK, so the fact is that the determinant of A, B, C is equal to this so-called triple product. Well, that looks good geometrically. Let's try to check whether it makes sense with the formulas. Just one small thing. So we saw the determinant is A1 times determinant B2, B3, C2, C3, minus A2 times something, plus A3 times something. I'll let you fill in the numbers. OK, that's this guy. What about this guy? Well, dot product. We take the first component of A, that's A1. We multiply by the first component of B cross C. What's the first component of B cross C? Well, it's this determinant B2, B3, C2, C3. Right? If you put B and C instead of A and B into there, you will get that the I component is this guy, minus, well, plus A2 times the second component, which is minus some determinant, plus A3 times the third component, which is, again, a determinant. And you can check you get exactly the same expression. So everything is fine. There's no contradiction in math just yet. OK? So, well, on Tuesday, we'll continue with this, and we'll start going into matrices, equations of planes, and so on. Meanwhile, have a good weekend, and please start working on your problem sets so that you can ask lots of questions to your TAs on Monday.